All right, so hello and welcome back. Our announcements for today are first and foremost, there's a quiz due today, and we're changing the way uh, we're turning it in. So we're going to be turning it into Sakai, which should be much simpler for you guys at least. And so the way that'll work is basically if you go to here, if you go to our Sakai page, then on the left here, on the far left, you should see this assignment thing, and yours will look different. Yours should look more like this. And you should be able to click on it and submit it. So you just go in here, you click choose file, you upload your completed file, and that should be it, right? So it should be much simpler, and it'll be very clear when it's turned in then. You'll even receive an email confirming that you turned it in. So let me know if you guys have any questions about that. Okay, so that's our quiz. Second thing is we have our usual homework due tonight. Then the next big thing that's coming up is exam 3 is 1 week from today. So I know it's a little bit shorter amount of time between exams than I had intended, but we're going to have to make it work. And on the positive side for you guys, there's only 4 sections that will be covered on the exam, so you can really focus on learning those 4 very well, and that might help you do better. And it'll be essentially the same format as the previous exam. And the last thing is that there is no class on Friday because it's a holiday for the university. Alrighty, so beyond that, do you guys have any questions before we get started jumping into section 4.2? No? Okay. So to get us started, let's think about an example like this. So where did it go? So our goal is going to be approximate, kind of similar to what we were doing last time. The area under this function, x squared plus x, using n equals 100 rectangles and right endpoints. Right now in Dakota, it's a little bit of both. But we're going to be mostly doing 4.2 today. Okay, so this may at first seem hard, and it actually is. If you wanted to do this out by hand, it would be very tedious to do 100 rectangles, right? But let's see if we could figure out how we would do it in theory, at least, right? So, first, just so we understand what's going on geometrically, I should have given you an interval. What's the interval here? Over the interval, say minus 2 to 6 or something. So this function here, you can factor out an x, and it's the same as x times x plus 1. So it crosses the x-axis at 0 and minus 1. So that means it's probably going to look like this. So let's see, minus 1 and 0. It's going to be an upward facing parabola. And, our graph isn't going to be perfect, but if we want to think about the area, we would imagine like 6 is over here somewhere. Minus 2 is over here somewhere. And so the area we would be interested in would be sort of this area plus this area plus this area. That's sort of what we're trying to estimate, right? It's not quite to scale, but I just wanted to give you an idea of what the picture looks like, right? So some of it is negative, some of it's positive, right? Okay, and then so our procedure from last time was to first, break the interval up. And so delta x here, the width of each little tiny interval, right? And we're going to break it up into a tiny little bunch of tiny little pieces here. Is will be 6 minus negative 2 over the number of pieces, which is the number of rectangles, which is 100. So this would be 8 over 100, or we could, let's see, it's 4 over 50, that's 2 over 25, if we wanted to simplify. And then we try to think about, on each of those intervals, like if we look at just what would the first one be? If we zoom way in here, we would be thinking about what's this interval, this tiny little piece. And so if this one on the left here is minus 2, then the one to the right of it will be minus 2 plus our delta x, which was what? 2 over 25. And then if you wanted to go to the next one, it would be minus 2 plus another delta x. So you would add another 2 over 25, right? And you could keep doing this. Okay. And so then if you think about like what's the right-hand side of the first one, it would be this one. So like the first rectangle would be, you would use the right-hand side, right? To get that rectangle. Okay, and so if we start writing that down, we would get that our area should be approximately, so each thing is going to have width 2 over 25, and then we just have to figure out what's the y values at the endpoints, or at our selections. So our selections here were right endpoints. And so the first right endpoint would be, whoops, that's not what I want, would be f of minus 2 plus our delta x, right? And then the next one would be and you could keep going like this. So the next one would be and right, you could keep going for a long time, right? There would be 100 of these terms. And the last one would be, the endpoint of the last one would be the very right-hand side of that one. That would be at 6. So the last one would be just f of 6. And so you'd have to, somehow plug all these in, right? And that sounds like a lot of work, right? And so today we're going to talk about sort of a way to organize this procedure and write it in a compact form that can be helpful to make this sort of process simpler once you get the hang of the sort of the machinery and the notation. So, because ideally we want to be able to do this for a very large number of rectangles, but we don't want to have to write out 100 terms, right? So there's a way to get around that. So what we have to talk about today is sigma notation. Sometimes called summation notation. And this is a way to write, when you add up a lot of terms that follow a certain pattern, you can use some summation notation to write it in a very short form or compact form that still has the same information. So let me just tell you kind of the definition. So for a function f and two whole numbers, whole numbers. Let's say we have m. So we have two whole numbers, m and n is bigger. Then we're going to have this new notation here. So you kind of make this big E, which is called a capital sigma. It's a capital Greek letter. And then you put some stuff beneath it and on top of it. I guess we're doing from m to n. And then you put your function here, like an argument. And let's see, so yeah, this thing itself is called a sigma. The n at the top is the ending index. I is the index. And m is the starting index. And the part that goes to the right of it is called the summand, though I don't tend to use that term much. I might just use the word argument or something. Okay, so this is some fancy new thing, and really what it stands for is it's defined to be, what you do is you start, so like this is a way to kind of repeat something many times. And so what you do is you first look at this part. This part is kind of your counter. It's just a thing that keeps track of where you are and what you're doing. So that's why it's called the index. And then you look at where you start. So we're starting at m. So that means the first thing you do is you plug in the starting index for I. So this is, so you plug in the starting index m for the counter at I. Then you increment I by 1. So instead of m, I'll go up 1 to m plus 1, and I'll plug that in. And then I'll increment my counter by 1. And so if you've ever done like a little bit of coding or something, you might recognize this as sort of like a for loop type of thing, and that's essentially what it is. So you would keep doing this until you get so when do you stop? So the top number up here, the n, tells you when you stop. Okay. And so you would go up until you hit f of n. Keep going up by ones, always by ones, until you get to the top number, n. And then you add all these. That's why we call it summation notation, is you have all these numbers that follow patterns, and then this is a compact way to add them all up. So let's see. So kind of like that. Right, so it's just a way of saying, if I know a pattern that my numbers follow. Like in what we did before, right? There was sort of this coefficient up here that was increasing by 1 each time, right? It was 1 in the first term, then it was 2, and then it was 3. So this will be sort of the same sort of idea. We'll be able to write this whole area thing as a sigma notation. Okay. So that was a lot of abstract nonsense. Let's look at just some examples, because that can be easier to understand. So let's say I have I equals 3 to 6 of 2i squared plus I. Okay, so you would read this aloud as the sum from I equals 3 to 6 of 2i squared plus I. And so what you do is you first figure out what's your starting index, 3. So then the first term that you get is you plug that in for I, for your index I. Right, so you would get this as your first term. Then you would go, so this was I equals 3, then you would go up to I equals 4, increment I. Oh God, why does this keep? And so if I plug in 4 now, you get 2 times plus 4, and we're going to end up adding all these. And so you would keep doing this until you get to 6. So we need 2 more. I said 6, but this should be 5. You increment it by 1. So it's for I equals 5, and then we stop when we get to the number that's on the top of this sum. Right? So we stopped at 6. Okay. So this takes a lot of getting used to if it's new to you. And then you would actually just figure out what these numbers are. I didn't write down what these numbers are. What are they? This would be 21. Whoops. 21 plus, and I'll leave the rest up to you. It doesn't really matter, but you could add these up if you wanted to, right? So let's do another one. Let's say I equals 0 to 4 of 1 over I plus 2. So it's the same idea. You would start now at plugging in, start with I equals 0, plug that in. Okay, that was let's make this maybe 1 over I plus 1 so we don't divide by 0. So then we get 1 over 1 plus 0 plus 2 as our first term. Then we would add to it, incrementing I by 1. And let's just make this smaller. Let's only go up to 2 because it's the same idea. So you would then increment I to be 1, plug in 1 now. And then you would increment I up to 2. Like that. And so this would be 3 plus 2.5 plus 2.333 repeating, right, 2 1/3. So whatever this works out to be, this is what, 5, 7, something like that. So you would get some number here, right? And so so the idea is you can often write adding up a bunch of things in this nice compact formula. right? You don't normally write it when it's just like 2 or 3 things, but if you had 100 things, that's when this starts to be useful, right? When you don't want to write out all 100 terms and they follow a pattern. Okay. Okay, so it's good practice to try to think about it in reverse as well. So let's think about it in reverse. So I'm going to give you some things that have been added together, and we're going to try to write them in sigma notation. In sigma notation. So A, we 3 plus 4 plus 5 plus 7. So why don't you guys take a minute to think about these? That one was wrong. There we go. Okay, so here's 3 numbers which have been written as, adding a bunch of things together, and we want to try to write each one as a sum or using sigma notation. So take a little bit to think about this and give it a try, and then I'll go through it. Okay. So it turns out that there are actually an infinite numbers of solutions to each of these. There's actually an infinite number of ways of writing these, but I think there's, at least for me, sort of a most obvious way of writing them. And so the first thing I would do is I would identify like what's the pattern between each term. So in part A, the numbers are increasing by 1 each time, right? They go up by 1. But that's exactly what happens in our sum, right? Each time we go to the next term, the counter goes up by 1, right? The index counter. And so the simplest way I think to write this would be to start with the number 3 and just take I as the counter itself, right? Because if I plug 3 in for I just get 3. And if I increment I by 1, then I'll be plugging in 4, so I'll get 3, 4. And then I'll have to go all the way up until I get to the number 7. Okay? Right, so here I'm thinking of this. This was I equals 3, this was I equals 4. And, the function was just f of I equals I. There are other ways you could have done this as well. Another way you could have done it, just to emphasize that there are multiple solutions, is you could have started counting at 1 maybe. And so if you change this so that the first term corresponded to I equals 1, and the second one was I equals 2, and so on, then how would you get from I equals 1 to 3? And like I equals 2 to 4, what operation does then? It's, if you think about it, it's adding 3, right? So this would be I plus 3, you know, and there are 1, 2, 3, 4, 5 terms, so we would have to have 5 terms here as well. So from 1 to 5 is 5 terms. So either of these would work. Wait, I did this wrong. It should be plus 2, right? Not plus 3. Right? 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5, etc. Okay, and if you plug the, an easy way to check that you ended at the right place is when you plug in the last one. If you plug in 5, it'll be 5 plus 2. You better get the last term here. Okay. Let's try the next one. Let's move this down a little. So this one has a different pattern, right? Each time I go to the right one term, the number gets multiplied by 3, and it switches signs, right? So you have to ask yourself, like, if this, and it may not be obvious where you want to start. So let's try just having this first one correspond to I equals 1. Maybe so. Then. And something that can help you see this is, if you start with the first term, how did you get to the second term? Well, it would be 1 times minus 3, right? And then how did you get from 1 times minus 3 to plus 9? Well, you could, if you think about it a while, it's the same as multiplying by minus 3, so that's the same as 1 times minus 3 squared. And this one turns out to be 1 times another factor of negative 3, so it's 1 minus 1 to negative 3 to the third. This would be to the fourth, and so on. And so now if you look at this, if you think about it this way at least, you could think of this one as being to the 0 power. And so what was the thing that was increasing each time? Each time I was multiplying by a factor of minus 3. And so that was increasing the exponent here by 1. And so the part that goes up by 1 each term is our I. So this means at least one way of writing this would be from I equals 1 up to 4. 1, 2, 3, 4. Okay, I guess there's 2 ways. There's sort of 2 ways you could think about this. Let me emphasize the way we just were talking about. So in there, this 0, we were thinking of this part as our I, right? So if that's the way we're thinking about it, then we would start it at 0, and we'd go up to 4. And it would be 1 times minus 3 to the I, where we don't technically need the 1 at all. Right? And you could check this, right? If you plug in 0, this would be minus 3 to the 0, plus minus 3 to the first, plus minus 3 squared. Right? And that'll give you 1, minus 3, plus 9, and so on, right? So yeah, it takes a lot of practice to get your thinking around this, but it's actually a very useful thing for calculating stuff. For the last one, what do we see? We see it has sort of a similar pattern. Like instead of just going up by a certain amount, it's doubling each time, right? Right, it's doubling each time. And in my mind, the easiest way to do it is to think of, if you start with the first term, what did you do to the first term to get to the second term? Well, you took 5 and you multiplied it by 2. Then how did you get from the second term to the third term? Well, you took 5 times 2 and you multiplied it by 2. So that gives you a 2 squared. And then how did you get from 20 to 40? Well, you multiplied by yet another 2. So this would say that the thing that's increasing by 1 each time is this exponent, right? So we could try writing this as the sum. Now we'd have to think about, like, what should the first exponent be? Well, there was no factors of 2 here, but we can always think of that as being 2 to the 0, right? So that means we should start at 0 and go up till 5 of 5 times 2 to the I. Okay, and that would be one way to write it. Right, so any questions about this? I know it can be confusing. Okay, so that's sort of the basics of sigma notation. Now this, just like derivatives and all these other operations, these summations have rules that you have to use when you're using them, right? You can't just take derivatives willy-nilly. You have to follow the rules. And so here are a list of the rules for summations. We're going to mostly just use this first one. So we're mostly going to stick to just these first two. And really what this is saying is, like, if you have the sum of 2i plus I squared from, say, I equals 3 to 11, it turns out you can split that up, just like you can split up a derivative, right? You can put the operation on each piece. So the summation operation, you can split into 2 pieces. You can just take the 2i plus the second bit, and you keep the bounds the same. The starting and ending, the 1 to 11 stays the same. So that's just a rule that these things satisfy. And if you wanted to break it even further, you can pull the 2 out, right? Just like you can pull a number through a derivative, you can pull a number through a sum. So you could simplify this as 2 times the sum of I equals 1 to 11 of I squared. So you could write it like this. And that will be useful for us later. And really the reason why this is true is, like, if you think about it, if you had something like, maybe it's not worth our time talking about that, but yeah, so the main idea here was, whenever you have a sum that has more than one term, like this had a 2i plus an I squared, you can break it up as a sum of the first thing plus the sum of the second thing. And if you have a number that's just sitting in front there, like the 2 here, you can always pull that out front if you would like, to make your life easier. Okay, so those are the main rules we're going to be using for sums. There are all these other ones that I put there just kind of for completeness. that we're not going to really use much. Okay. So that's the properties of sum. And these are on the summary sheet if you don't want to copy them down. Okay, so before I show you that, let me just ask you a question. What is 1 plus 2 plus 3 plus 4 plus 5 all the way up to 100? So what if I add up the first 100 numbers? What do you guys think that is? Because there's a cute little story about Gauss was a mathematical prodigy a long time ago in like the 1800s, and supposedly when he was in grade school in like third grade, his teacher was kind of sick of dealing with students, and he gave his class this problem to keep them busy for like a half hour. Right, they're third graders. You wouldn't expect them to do this very quickly, and Gauss came up with the answer in about like 15 seconds or something. I don't actually believe the story's true, but that's what everybody says. But there is actually a way to see what this is fairly easily. So let me show you the trick. So the trick is, what does 1 plus 100, the outermost two terms, add up to? They add up to 101, right? Now if I go to, so maybe let's put a couple more in here. So if I add up the next inner two, 2 plus 99, that's also 101. If I go in again, that'll be again 101, right? So how many pairs like this are there? Well, I'm pairing things up. So there's 100 numbers in total, so there'll be 50 pairs. So the answer should be 50 times each sum is 101. And so that's what 5,050. Right? So not too bad if you think about it that way, right? And so, yeah, this is what we would call a summation formula. So what we just proved, or well, we saw the idea behind the proof at least, is we saw the idea behind number 2. Right, because number 2 is really asking the sum from I equals 1 of I to 1, right? This is just 1 plus 2 plus 3, and you keep going until you get to some number n, which you can choose to be anything you want. Here, before we had 100, right, for our n. And what it turned out to be was a 100 over 2, that's the n over 2, times 101, right? That was our 50 times 101. And this was for n equals 100. Okay, so you can prove that you can prove like there's quick ways to add these things up instead of just doing it by hand every time. Like if you don't want to add up all 100 numbers, you can just do this quick multiplication. So these are called summation formulas. And so these are the ones I expect you to know. So the first one basically says, so more concentrate on this one. So this one says, so C is supposed to be in numbers. So let's say if C was 5 and N was, maybe 4, what would this look like? So it would say sum from I equals 1 to 4 of just the number 5. Well, we know what that would be, right? If I plug in 1 to the function 5, it's just 5. If I plug it in, plug 2, you increment I by 1 up to 2, you plug that into 5. Well, there's no i's, so it's just always 5. So you get 1, 2, 3, 4 of them. And if you think about that, right, if you add up the same number repeatedly, that's the same as just doing 4 5s, 4 times 5. So that's what it's saying. It's saying if you add up the number c n times, you just get the number times the number of terms you added it up. Okay. And then we have formulas for if you add up the first I integers, for like 1, 2, 3, or you could add up the first n squares. And that has this more complicated formula. So I would like you to memorize the first 4. Okay, though I guess because I'm giving you notes, normally I would ask you to memorize them, but I would still recommend getting very familiar with them. And the last one is, if I added up all the cubes. So these are just 3 of them that turn out to be fairly simple. If you're just adding up a bunch of random things, it can be very hard to find a formula for it. Okay. All right. So those are summation formulas. Well, let's try using them a couple of times. And again, these are on one of the summary sheets. I forget which one. But let's try using them. So, how much time? We got a half hour. So let's compute the sum. The sum from I equals 1 to 30. So this is probably something we would not want to do by hand, right? Because you'd have to add up 30 numbers of 3i plus 1. Right, so remember, this is just shorthand for having 3 times 1 plus 1 plus 3 times 2, right? You increment I by 1. And you would keep doing that all the way until the very last term would be when you plug in 30. 3 times 30 plus 1. So we're asking what that's equal to. And what you would do is you would first use the property we talked about before to split this up. So this, you would break it up into 2 pieces. And you would pull the 3 out. And the top and bottom parts always stay the same when you do this, right? They're always the same. Those don't change. And so I have to put a 1 here. Whoops. A 1. Okay, and now we're in so basically the idea is, just like when we took limits or derivatives or something, there were some very basic things that we knew how to do, right? So these are the formulas, right? These are the formulas are the things we know how to do up here. So if I look at the first one, I see I have a sum where I just have an I here. Right? And so that means if I go up to this formula, I want to use the one that just has the I there. Okay, and now I have to figure out, well, what's my n? Well, n is the thing that's up here. So in our example, n was 30. I wish it was easier to go back and forth between this. Okay, so that means I have to substitute in this other thing which it's equal to. So it's n plus 1 over 2. So that means I can replace this with 3 times n, which was 30. N plus 1 is 31 over 2. Right, so instead of having this complicated thing which asks me to add up 30 things, now I just have this number, right, which is much simpler. And that's why these formulas are nice. Okay, and then the second one, it says so remember, this one would just be like if I add up 1 30 times. So that was an example of this, this one up here. And so it's just 1. It's just 1 times the number of times you've added it up. So this will be 1 times 30. And then, yeah, you can figure out what that number is if you want, right? You'd have to throw it into a calculator, I guess. It doesn't look like a nice number, but you could throw that into a calculator very easily. Whereas throwing the sum into a calculator, you don't want to type in 30 numbers, right? Or, yeah. All right. And let's do one more. Stop me if you have a question. So let's compute one more of these. Okay, say I had the sum of this. So this would ask you to add up 300 terms. So that sounds horrible to do by hand, right? But we can do it fairly quickly with the formulas. We didn't prove these formulas. We saw why the second one was true, but we didn't really talk about the third and fourth. Those are harder to prove. But you can just take for granted that somebody else has done the work for you, and you can use them. But we would follow essentially the same idea. You'd break this into 2 pieces. Keep the bounds the same, 1 to 300. I can pull the -8 out front and just leave anything that involves an I, right? The one rule is that i's cannot come through a sum. Well, more specifically, like whatever's here cannot pass through a sum, right? So if it's something that involves an I, you can't pull it through. But if it doesn't, then you should be able to, unless it somehow depends on I. So this should have it cubed. Whoops. So we could simplify the first term as this. Then we'd have a minus. We could take it and split it up like this. Of just I. And then these things, like this thing here has a formula, right? This is one of the things in our formula list. This is a different thing in our formula list, right? So if you look at it, we're going to be able to replace those with just numbers instead of big sums. So let's go figure out what we should replace them with. Well, we saw the second one already, right? That one you replace with n plus 1 over 2. So n here was the 300. So it'll be n, which is 300, n plus 1, which is 301 over 2. And then the I cubed one is a different formula, right? We haven't used that one before, but if you look over here, it'll be n plus 1 over 2, so it's actually the same formula squared. It's kind of a curious phenomenon. It's interesting to think about why that is. It's actually not easy to see. So we would do that. So it's going to be essentially the same thing as what it was before. 301 over 2, but now all that has to get squared. So that's squared. And that's something you could easily type into a calculator, right? Whereas the one above it, you couldn't easily. Okay, so that's a little bit about how to compute with these. Okay. Okay, so we're going to have to get back to using these with the area stuff, right? Because the whole reason we started talking about this was to talk about areas. And so let's remember that the general idea we talked about last class. Let's see, where should we do this? So what we talked about last class is, we can approximate areas using rectangles. And we learned how to do it for 5 or 6 or 8 rectangles, some small amount of rectangles. Today we want to understand how do we do it for a very large number of rectangles. And so this kind of the second piece of this is as, more rectangles equals more accurate. Okay. And so the idea that we're going to get to now is that the exact area it's going to be a limit where n is the number of rectangles. So we're going to see what happens when there's a very, very large number of rectangles. So you look at what happens when you approximate, using 100 rectangles, you get some number. You approximate using 500 rectangles, then 1,000, then 1,000,000, then 1,000,000,000. And you try to understand what pattern is happening in those numbers. Are they approaching a single number? And that single number, if it approaches anything, will be the exact area. So it's asking if you first just understand how to approximate using a certain number of rectangles, and if you can say that for an arbitrary n, and then figure out what happens as you make that number really large, it'll tell you basically what the exact area is. Maybe I should put the word rectangles in here. So that's going to be the idea today. But before we can get there, we have to write everything in terms of summation notation. So our approximation using n rectangles and so when we do this sort of process, we're going to always stick to using right endpoints. You could do right, left, midpoint, upper, lower, but we're just going to stick to one because it always works and it's just the simplest. So we're going to stick to right endpoints now. So we're going to try to approximate areas with n rectangles. And so remember, the idea is, you have some function. You have some interval, a to b, where you want to understand the area. And what you do is you break it up into a little bunch of little pieces, right? And now we're going to take the right endpoints always. So the first right endpoint would be here. Right. Okay, but how do we write this as a sum? Okay, so the first observation would be that it's, the width of each of these will be delta x. Right, so we're going to just try to write everything a little bit more abstractly. So each one has width delta x. Then the heights are given by the right endpoints. So remember, it was f of a. So the first one would be a plus delta x, right? Because it's the right one. And the second height would be a plus 2 delta x. And so you would keep increasing the number of delta x's you go to the right until you get to the end. Which a fancy way of writing that would be n delta x's, because you split it into n pieces. Okay, so that's kind of the long-winded way. If we write this in terms of a sum, if you think about it, this is the same as saying delta x times the sum. And now which thing was increasing each time we went up a term? It was the 2 went up to a 3, went up to 4, 5, up to n. And so there's sort of a hidden 1 here, right? Think of there as that just being 1 delta x. And so what goes in our sum is f of a plus I delta x. Okay, so this is sort of a formula we're going to be using. More commonly, we're just going to write it out a little bit more explicitly because we'll just paste in what delta x is. Oh, and I should put bounds here. I equals 1 to n. So our approximation using n rectangles is this. Okay. So this is really the one you want to know. It's just a fancy way of writing what we were doing before. But now we can use the power of sums and these formulas and stuff. Just a comment, you may also see it written quite often like this. So instead of writing a plus I delta x, you might just see x sub I star. So remember, these are selections from ith interval. It doesn't look like a word. So it could be the right endpoints, it could be the left endpoints. This is sort of a more generic version. Whenever we say x sub I star, we're usually going to mean a plus I delta x because that's the right endpoints and that's the easiest one to use. Okay. Okay. So now putting that together, so that was just an approximation using n rectangles. Then going back up and using this idea, we want to see, well, what happens to whatever number that this gives us as n goes really big. Okay, so the moral of the story here is that, let's not do this in red, is that the exact area is the limit as n goes to infinity of this business. So you've got all these sort of complicated operations now mixed in with each other. But you got to live with that. It's the way it works. So this will be our exact area. Okay. And because this is such an important idea, it's given a name. So this is going to be called the definite integral. Okay, and hopefully you have time for one of these examples. So the definite integral just says the signed area. A lot of times we don't say the word signed, but it's sort of implied. Between an integrable. So there are certain functions which you can't actually compute the area of, but they're so ugly you could never almost write them down. So we're going to kind of ignore that idea just for the sake of time. But most functions we can actually find the areas under, and they're called integrable. So the signed area between an integrable function and, let's maybe not underline that, and the horizontal axis or x-axis is, so we get a new symbol. So a lot of symbols today. I should give an interval over a to b is called the definite integral, and now you make this big long S looking thing. And then you put your function. So maybe it's best if I put it like this. So, this symbol, what I've written here is the operation of taking the area, and then you can insert stuff where I've put this yellow, right? Is you're asking like, what am I taking the area of, right? So, this symbol takes the area between a and b, and so if you're doing that of the particular function f of x, then you would put f of x in here. So this symbol is called an integral sign. Now the a is called a lower bound. Maybe we should do these in a different color. This is the lower bound. This is the upper bound. And this helps you keep track of what variable you're doing. So just like when sometimes you have to worry about which derivative you're taking. Sometimes, if it's ddx or ddz or ddt or something, this is the sort of the opposite version of that. So this is called the variable of integration. And I don't use this term much, but this is called the integrand, this f. It's the thing you integrate. Okay. And so this is just a new symbol, but what it really stands for is it stands for the area we've been trying to compute. And the way you compute it is you compute it using this fancy limit of all these sums. Let's just write it with the way we were writing it, as b minus a over n sum I equals 1 to n of f of a plus I times b minus a over n, like that. So that complicated thing. And just another piece of terminology, this part inside the limit, this has another name. These are called Riemann sums, because the guy that invented this process, or at least laid it out very clearly, was his name was Riemann. Okay, so we figured out how to calculate the exact area, and then we've given it this integral symbol as a fancy and quick name for it. Okay. Blah blah blah. What do we have time for? Okay, so I don't have time for a thorough calculation, so let's just go with this. So let's do this example. Compute this integral. Let's say from 0, let's do -1 to 4 of 3x plus 3. Okay, so remember what this says, what this whole fancy symbol stands for is it stands for compute the area under the function whatever's in here. That's always your f. And then you have over the then you have an interval. And the interval is always from the bottom number to the top number. So always from here up to here. Okay, and so if you had no idea what this was, you would have to go through and do this whole horrible limit of the sum thing, which we will talk about, looks like probably after our exam. And but there's a quicker way to do it, at least in this case. Right, so if you draw the graph of this, right, 3x plus 3 has a y-intercept of 3, and it goes through 0 at minus 1. So here so our interval would be from minus 1 up to 4. Right, so the area we would want to calculate would be this area, right? But that's just in the shape of a triangle, right? So this has area 1/2 times the base, which will be this width, which is a width of 5, times this height. And well, you have to think about, well, its height is whatever the y value is here. So that'll be 3 times, if I plug in 4, I get the y value. So that's 15. So that's what this answer is. Right, so this thing's just a fancy symbol for taking areas. And it turns out that that's related to antiderivatives, which is what we were ultimately interested in. Okay, so I think we're going to leave it there unless you guys have questions. It is quite a complicated section, right? So I do encourage you to ask questions.